Good day, everyone. In this video, let us discuss the stationary states in quantum mechanics. In classical mechanics, if we consider a particle that travels in space and time, the description of the system can be provided by the Newton's second law of motion, wherein the net external force is equal to the product of the mass times the acceleration. But the acceleration can be expressed in terms of the second order derivative of the position r with respect to time t. So if we can provide the net external force on this particle, substitute that to the force, then we can solve this differential equation and we can provide the position of the particle as a function of time. And that position with respect to time can be differentiated and we have the velocity. Okay. Meaning if we have a position, take the derivative of that with respect to time, we can solve for the velocity. And also, if we have a velocity, we can also solve for the acceleration. And so with momentum, energy, and so on. Now, all the quantities are determined. Why? Because this particle is a kind of, or the system is deterministic, which means that we can locate the position of particle at initial and we have the final and we can provide the trajectory because the system is deterministic. All quantities are determined. On the other hand, in quantum mechanics, the system is composed of tiny particles, very, very small. It can be a microscopic, nanoscopic, as long as it cannot be seen in our naked eye, but we know that there are particles inside the system. So if it is a very, very small, then we don't know what kind of particle is that. We cannot label each particle and identify that a particle A or particle B. So therefore, we cannot locate the initial and also the final position of that of each particle. Hence, that this system is indeterministic. So because this is indeterministic, there's no initial position. We don't have the final position. And of course, we don't have the momentum. We have the definite momentum and definite energy. Therefore, this system cannot be solved using Newton's law because Newton's law can be applied only if the system is deterministic. Now, remember that our technology relies on the theory of quantum mechanics. We need to provide the description of that system. We need to give information of that system in order to come up with an idea in terms of technology. So, for example, we need to know the behavior of these atoms and atom and molecules. Of course, the system cannot be solved using Newton's law. And also in a crystal lattice, if you want to know to know how much is the vibrational frequency of the atoms inside the crystals, and also if we want to know how much total energy in the crystal system, then we need to solve this, and we cannot use the Newton's law. And also in the material science, we need to study about the surface, the catalytic material. So it requires surface. With that surface, we need to know how much is the ability to absorb outside molecules, meaning if it can interact. So the amount of absorption will dictate the capability of the surface, the catalytic ability. The greater the absorption, the greater the more precise or good material for catalysis. Okay, so therefore we badly need to solve these systems. Okay, so if the Newton's law cannot provide the description of this quantum system, then we have the Schrodinger equation. The Schrodinger equation is a form of differential equation, second order differential equation. And we have this function, we call this as the wave function. So the wave function depends in position and time. And we have this partial because we have two variables. And we have this potential energy. And we have this constants. And we have the mass. Okay? So therefore, in order to describe the system, we need to solve the wave function, the big psi. When I say big psi, it is position time dependence. So after solving the Schrodinger equation, if we have now the big psi, then all we need to do to describe is to take the absolute square or the modulus of that wave function, big psi, we call this as the probability density. And this probability density is the possible or the probability in the system. Now, if we take the integral of this probability density uh, from certain interval from A to B, for example, then we can calculate the probability of having that particle in that kind of interval from A to B. So it is already a description of that. Now, this idea is coming from the Born statistical interpretation. So since the system is indeterministic, meaning we don't know the position and we don't know the momentum, then all we can do is to have the statistical interpretation of this system. Now, aside from that, as the probability of having that particle, we can also provide the description, the so-called expectation value, meaning it is the average of particle for a given interval. Expectation value is the term that we use in quantum mechanics. So it is equivalent to the mean value or the average value. So which means that if we have the big psi, we can provide the expectation value of the position, expectation value of the momentum, expectation value of the energy, and so on. All the dynamical quantities can be solved if we have the psi x or the big psi. So therefore, it is badly to solve this differential equation, the Schrodinger equation, solve that in order to provide the big psi. And with that, we can describe the system. Okay? So, but sad to say that if we consider a real life system, meaning in a real system, Schrodinger equation is very impossible to solve. We cannot solve the the time dependent Schrodinger equation if we consider the position time dependence. Why? Because when you look at the first term, this is a second order differentiation of the big psi. Okay? But this is the kinetic energy, the total kinetic energy in the system. And the kinetic energy are the following. We have the kinetic energy of the electrons that travels within the system, and also the nucleus, the nuclei, the kinetic energy of nuclei, summing up with the kinetic energy of electrons, we have the total kinetic energy of the system. And remember, for every particle's kinetic energy, it is a function of position and time, and also with the nuclei. The second term is the potential energy. This is the electrostatic interaction between the particles in the quantum system, meaning the interaction between electrons and nuclei, and also electron to electron interaction. So we have the electrostatic effect of the electron-electron and also the nuclei-nuclei effect. and all of them are a function of position and time. So summing up that that uh, interaction, we call that as the total potential energy within the system. The right member is the total energy of the system, which is again a function of position and time. And we can notice that the total in the Schrodinger equation, the total energy is the sum of the kinetic energy and potential. This is consistent with our idea in classical mechanics. Okay? So, very difficult to solve. Why? Because of the position time dependence. And we have a lot of particles in the quantum system. Okay, but we need to solve that. In spite of difficulty, we need to solve, whether we like it or not, we need to solve the time-dependent Schrodinger equation. But what's the step? Or what will you do in order to solve this? Of course, we make the complicated to become as simple as much as possible. Meaning from the very complicated, we make the differential equation to be a simple equation. Okay? Now, uh, take note in classical mechanics, we have a so-called uh, idealized model in projectile motion. If we consider the system in projectile motion, if we consider all forces that acts on the particle, the projectile motion cannot be solved, or it is a very difficult. It cannot provide the analytical solution of that. If we consider everything, that's why we have the idealized model, and we assume that the particle travels in space is already only influenced by gravity, and we ignore the resistance, the Coriolis effect, the effect of rotations of the particle. We treat the particle as a point particle only and ignore other effect, and we consider only the effect of gravity. Then the problem becomes simple, and we can provide descriptions. We can provide the trajectory of that particle. And if we consider only the gravity, the trajectory, in fact, is a kind of parabolic. Now, remember, parabolic, it has the point of symmetry. So it becomes a simple to describe that system. In thermodynamics also, we assume gases as ideal gas. And remember that there's no such thing, gas as ideal. Ideal gas does not exist. Also with the idealized model, which is the force of gravity only, it doesn't exist. But the idea of having that assumption is very much important in technology. Okay? Now here comes the quantum mechanics. The problem in time-dependent Schrodinger equation. Very difficult to answer. Why? Because the equation is a very uh, complicated. So therefore, in similar way, we will make this as simple as we can. So the first assumption, the first attack in quantum mechanics to solve the Schrodinger equation is to assume that the potential energy of the system is a function of position only, which means it does not depend in time. So the changes of the potential energy depends on the position of particle. Now, if that's the case, then it follows that the wave function depends only, or the wave function can be split, or the big psi can be split into two kinds of wave function or state. We have the psi x, the big, small psi. When I say small psi x, it is a small psi, and we have this big psi. Then multiplied by phi, which is a function of time only. So, meaning this is a kind of separable solution. The differential equation now is a kind of differential separable. If we assume that the potential energy is a function of position only, then we have these stationary states. So, when we say stationary state, it is a system that has the uh, description of having separable solution of states. We have the psi x and we have the pt, where the psi x depends on position, pt depends on time only. So with that, this is if we substitute this uh, to the time dependent Schroeder equation, then that equation becomes simple. Okay? So therefore, our learning outcomes in this video is to derive the generalized stationary state. We will derive the stationary state in the quantum system by solving the big psi. So to solve the big psi, we need to solve for the stationary states in position and time. So therefore, operation solve psi x and pt. Multiply the two equals the solution to the stationary state. We will derive the uh, stationary state. Another thing is we will provide the calculation flow of the stationary state. Meaning, what will be the solution flow? Where will you start your solution in order to uh, describe the system? For example, if you have the infinite square wave, what will you do? What is the first attempt that you need to provide? Okay, so this is our main or learning outcomes. So let's going back to the previous slide. Remember, we assume that the potential energy depends on position only. Hence, the big psi is a kind of separable solution of states. So substitute this psi x and pt to the big psi in the time-dependent Schrodinger equation, and this is now the result. Okay? So the first term, remember, this is a partial derivative square, second order with respect to x. And we have this wave function. Now, in this case, only the psi x will be affected by differentiation, and the pt does not depend on x. So we can move this out of the equation, and also this partial differentiation will reduce to ordinary differentiation because we have only one variable. So therefore, this will be the outcome. Okay. The second term, we can do nothing, but except we can remove the grouping symbol. And the right member, take note that this is with respect to time. Hence, the psi x does not depend on time. So we can move it out of the operation. Okay. So therefore, this is it. No. Okay. Next step. We are done with substituting the big psi with the uh, stationary states. Then our next step is to separate, because this is a kind of separable equation. So we will separate the psi x and pt. And to do it is to apply the idea or ability in mathematics. So uh, we can do it by dividing both sides by psi x and pt. So nothing has changed because if you divide this with psi x and pt, the same divisor in the right number. Okay? Now, in mathematics, we can simply split the denominator or the fraction. Then notice that we can cancel something. We can cancel the pt, the first term. In the second term, the psi x and pt can be totally eliminated. While in the right member of the equation, psi x can be removed. Hence, this equation will reduce to that. Okay? Now, the good thing is this right member, which is the function of time only, and the left member is a function of position only, meaning we successfully separate the variables. Okay? Another good thing is this one, the right member, is just equal to the energy of the system, meaning the total energy of the system is just equal to this expression. The I, it's bar 1 over P, D P over with respect to time. So meaning we can replace this with E and this is the result. Okay? So if we multiply both sides by P to make it simplify as further, then of course we have to multiply its term by psi x, and this is it. We have this one. So meaning we can cancel this psi x. Okay. So therefore, this equation will reduce to this result. Now, these two equations is equivalent to the time-dependent Schrodinger equation. Okay? So, this very complicated time-dependent Schrodinger equation, which is a function of position time, is equivalent to this two differential equation. But take note, this is only for a system having the ability to come up with stationary states. Otherwise, we cannot use this. Okay? So, in other words, the one equation becomes two, but this two is now handy compared to the time-dependent Schrodinger equation. Comparing the one and two, the one is a very simple differential equation. We can solve right away the PT because we need to solve, in order to solve big psi, we need to solve for the stationary states. Diba? We need to solve for psi, PT and also the psi x. So in equation 1, we have this PT. So we will solve this. And this is very simple because this is separable again. So we will separate the variable, meaning we will isolate the constant because E is constant. Then also the dt, multiply that. Then combine only the pt on the right side. We have the option to revert the order of this left and right position. Nothing has changed because this is still sign equality. Then, to solve for p, we need to integrate both sides. That's the good thing of having separable equation because we can directly take the integral. Okay? So since integrate both sides, then it should be distributed left and right. Now, take note that the integral of the derivative of p with respect over p is just the natural logarithm of p. An integral of dt is very easy, it's t. Now, since this is indefinite integral, so we need to add constant of integration. So, in other words, this is now the evaluated expression of the differential equation. Okay, now remember our goal is to solve for this. And this is a kind of logarithmic form of equation. Okay? So, we will convert this to exponential because for every logarithmic, we have the corresponding exponential, vice versa. But before that, the I is in denominator, we have the option to move it up in the numerator. But take note, we take the additive inverse. Okay? Now, another thing is the natural logarithm of p is just equal to the log base e, the Euler constant of the pt. And we have this right member, which means that if we convert this logarithmic form into exponential form, we can have this guide that this base has the exponent of this expression. Entire right member is the exponent of e, and it should be equal to the number of logarithm. So meaning, we can solve for the p, and that's the result. Okay? Now take note, we have this constant of integration. So, but we can break this exponential into two factors. Okay? Because plus means you have to multiply. If it's minus, you have to divide the expressions. Okay, but what is e raised to a constant number? E raised to a very large number. This will become a large number. So we can put that c. Okay? So therefore, this is the solution to equation 1, the differential equation 1. Which means that we are now ready to provide the description if we have this value at any time. Okay? And take note, this is I. Now, I is in exponential form. If we have I here, this is an oscillatory behavior of the function. So meaning, this can be in terms of sine and cosine, sinusoidal. So therefore, again, this is now time dependent. So we call this as the wiggle factor, which means that wiggle factor is one solution to the time-dependent Schrodinger equation in stationary state. If we have this E. But remember, this E is the same as E in the second term, the second equation. Okay? So we have already this one because this is a very easy differential equation. But when you look at this one, this differential equation, this is actually a very popular equation. We call this as the time-independent Schrodinger equation or the TICE. Okay? Wherein, if you want to solve for psi n and energy simultaneously, we need to know what is this potential energy. Now, if we have this potential energy, then we can solve for the psi x and E. Okay? And this potential energy depends on different systems, meaning different systems have different potential energy. We have the potential energy in an infinite square well or particular box. We have also potential energy of the harmonic oscillator, the finite square well, and so on and so forth. Okay? So therefore, if we have this, then we can solve for the psi x, which is the time or the position dependent, and also the energy. So since we solve the energy, then this energy will be replaced here, and we have this one. Okay? And it depends upon the system. So assuming this is now the psi. So therefore, the big psi now can be solved because we have this psi x and we have to attach the wiggle factor. So this is now a position time dependent of the wave function in Schrodinger equation. We are able to solve the wave function because of the assumption of having separable or the system is an stationary state. Okay? So, but remember that C, constant integration, can be absorbed by the wave function. So meaning, remember the wave function have also wave function. So meaning, we can absorb that. To make it simple, the psi x, the big psi, is just equal to psi x times the wiggle factor. And remember, this energy depends on system and also with the psi x. Okay? So, as I said, now, here is the flow. What will you do? If you're not given the system, what will you do? What is your first step? Okay. First step is to know, di ba, the generic problem. So it should be a system that complies the requirement of having stationary state. So you have to analyze if it is a stationary state system. So therefore, after that, then of course you have to identify the initial wave function. When we say initial wave function, it is the wave function at time is equal to zero. Then the goal is to solve for the wave function in position time dependence. Okay? So to do it is, of course, identify the system potential energy. So you know that it is a system, quantum system that has the ability or belongs to the stationary state system. Then identify what is that potential energy. Then after that, substitute that potential energy to the ties. Then solve this differential equation. Then if you solve this differential equation, we can solve for the psi and the energy. Okay? Now, if we solve that, then it can be a form of multiple psi, meaning it is not only one value. It can be two or more. Okay? Now, for every psi that you calculated, there is a corresponding energy. And we call this is actually an eigenfunction, and this is eigenvalue energy. So therefore, for every state, we have the associated with energy. Where n is the quantum number, so n will start from 1, 2, 3, going to infinite. Then its level of energy, our state, we have the level of energy. Hence that if you are looking for the complete solution of this stationary states, you need to sum up all the states. meaning sum up psi 1, psi 2, psi 3. But for every summing up, for each state, we have the so-called expansion coefficient. So Cn is the expansion coefficient, meaning we have C1 times psi 1 plus C2 times C2 and so on. Okay? So meaning taking the sum is actually the complete solution because in stationary states, the complete solution forms the linear combination of state. But take note, we have the coefficient of linear expansion. Okay? Then after that, if you have that result now, then attach the wiggle factor and we call this as the generalized stationary states. I call this as generalized. Why? Because this is the generic flow or this is the usual flow in order to solve for a system that has the stationary state capability. Okay, so if you solve the infinite square well, you have to follow the system. If you solve the quantum harmonic, then you have to use this system. And this is true to all a stationary state. Okay, so that's it. We derive the stationary state and we provided the flow and we come up with this generalized stationary state. Okay, so for your assignment, okay, try this. No, find the stationary states of a finite square wheel, or simply we call this as a particle in a box. In a particle in a box, we have this system wherein zero energy inside, but infinite energy outside. If we have the infinite potential energy, then it means to say that the particle does not exist. Now, infinite because the potential energy, the whole is going to infinite. So you can imagine a system that has a very high wall, where no way to escape. Okay, so therefore, the particle inside the box is a kind of a free particle. We don't have energy, potential energy inside. So therefore, we have the particles, but in different levels. So our goal is to solve what is the state with respect to the quantum number. So derive. Okay. So therefore, since the potential energy outside is zero, our infinite, so meaning zero psi, zero on the right side also. So we will focus only inside. Inside, the potential energy is zero. So therefore, the starting solution now, we have this generic problem. Okay. Then we identified the the potential energy, and that potential energy will be substituted in here. Okay. Then once substituted, then we can now solve for the psi. Okay. So take note that the result of this is a series of psi. Psi 1, psi 2, psi 3. Then of course, combine it with the coefficient of expansion, then we can provide uh, the psi. Okay. Of course, we can attach the wiggle factor and take note that we need to solve for psi n. The psi n, this one, the psi n, the coefficient of expansion, linear expansion depends on the system. If you are in an infinite square well, then we have to use the Fourier trick. Okay. In quantum harmonic is another also equivalent for psi n. So therefore, it depends upon the system. Okay, so try also the harmonic oscillator, wherein the harmonic oscillator has the potential energy of 1/2 m omega square x squared. Okay, where omega is the frequency, uh, angular frequency of the uh, quantum harmonic oscillator. Okay, then substitute that to the ties here, then of course continue. Okay, so I think once solved, then that's it. So I think that's all for today. Thank you.